Okay, so let's continue. So now I'm gonna just cover briefly about multitasking in mobile systems. So these are your smartphone, the tablet, and so the user interface is much more important, and the user experience is important. So starting with iOS, initially they had the foreground process that controls the user interface, and then most other things are in the background. And so initially that was just single task, and background process didn't get any time. But over time, there's need for, like, if I want to continue updating, continue downloading, and also then there's tasks that need to run in the background, and or respond to certain events. Okay, and these are all done in the name of saving power, improve responsiveness. So the policies are slightly different from your desktop or general purpose systems. Now Android, on the other hand, started with a Linux core, and so one of the first things they had to do was really to make changes to be more battery friendly. And Android supports much more in terms of running multiple things at a time. But of course, the price to pay is the battery would suffer just because OS starts eating into the overhead. So then they started developing more a structure so that it's really an agreement between the application and the OS, in that a lot of times OS reserves the right to take control back, give less time slice, or even suspend, put a process on hold if it's not running in the foreground. Right? Or limited to whatever it can do, like no user interface, but maybe keep memory. But then, like iOS actually can purge your state or save to non-volatile memory when you're in the background. And so so mobile systems do it differently. So you can read more on your own. I'm not going to test you on this. So context switching, key concept, save state of the current running process, and then pick one, restore its state, right? And then where you save the state, PCB, right? For overhead reduction, there's different ways to do it. Some CPU provide support in terms of saving, restoring registers, maybe in the form of these instructions or register windows, and allowing multiple contexts to be loaded at the time. Okay, next I'm going to talk about operations on processes. So these include a creation, termination, in addition to switching. Okay? So creation is done in the form of fork and exec on Unix system. Windows has a different way to do it, but I'll just mention that in a little bit, mainly focusing on Unix way of doing things. And also termination. Now termination could be in terms of exit or some kind of abort, or actually there's also a separate kill. And then wait is to for somebody who starts a process to wait for a child process to terminate. Okay, so in Unix and a lot of other systems, process creation is done in the form of this kind of parent-child relationship. So as opposed to Windows is more like you create a process, and but you load in the whichever program image to run and other things. So it's a lot more evolved, a lot more involved. In Unix, think of it as one process kind of making a clone of itself. So like giving birth, right? But it looks just like the parent. So that's why there's family tree, so that way. But then, of course, once it's created, you can change it, replace it, whichever you want. But at least that's the initial idea. Okay, and so in Unix, what you start out when you first boot up is a process with PID 1, and that's called init. That's the boot up process. Okay, and from init with PID 1, then it clones itself, but then as soon as it clones it, each one gets replaced with something else. And so they form a parent-child relationship. And later we'll see why this parent-child relationship is important. And each new process would have a unique ID called PID, usually an integer. Okay, and if you want to see what processes are currently in your system, you do PS minus some flag. And AEL is, I think, the one that works with most systems. So A for all, and then list for long. You don't have to use long, you can just do the other, but it shows less information and other things. Okay, so now, when you create a process in this kind of parent-child style, you do have some options of resource sharing. You could share all resources, or the child could share a subset of the parent resource, or no sharing at all. And these are all possible options. An execution option could be that you make a clone and then they both run as equals in a way. And the other way would be more like a shell style. I'm a shell, I launch a process, run, and I don't do anything in the meantime, and until that process finishes, right? And then when it finishes, comes back, and then shell gets control, right? So there's that style. Parent wait until child to terminate. Now, what about address space options? Well, conceptually, each process, even as a child, should have its own address space. But what about the initial content? So in the case of Unix, you use a fork. A child gets a complete duplicate of the parent's memory content, including its program counter, except for a tiny little part that's different. Okay? So child runs the same program image as a parent. In fact, all its stack, all its heap, globals, everything, a program counter, even program counter is exactly the same. It's a clone. So wherever the parent runs, then there's the fork. And when you have a child, that's the exact clone. So when the child gets resumed, it starts running from that fork, continue down, okay? It's like, well, why would you do that? Well, there's good reasons why you want to do that. Because that actually gets the parent a little bit of control over what the child is supposed to do. A lot of other things are actually much easier. I think you might say it's for ease of programming. We'll see why that is the case. Now, if the parent and child need to communicate, you may have to set something up. Again, the parent does have a little bit of control over the initial stage of the child. Okay? And then once it's set up, then it can do whatever. And they could communicate over a shared variable, but it's not automatic. You have to set it up. Now, child program, another option is it's not a duplicate. So that's more like in the case, I mean, you could do it Unix way too, but at least the fork mechanism could be used in conjunction with what's called exec. So as soon as the parent makes a clone of the child, what it does immediately is the child actually doesn't have control because it's still running the same code as the parent. So then the parent can decide, am I a child? Am I the child and am I the parent? It can make that decision. And then, so that's the part where the parent has the last control. Then it can decide, okay, now because I wanted to run I launch this program, then replace it with a totally different program image. So that then that replaces it and runs, restarts it. So that's really the Unix mechanism. And then if they need to communicate, they could communicate, well, by shared memory or by message passing. Okay, either way is fine. So the magic is this system call called fork. And what that does is the parent clones itself. By cloning, that means making an exact copy except for one little thing. That's the return value, okay, of that fork. So you can call fork, and then so child process duplicates the address space. That means it makes a copy. Conceptually, it makes an exact copy. Okay, so including your everything, even registers, even your stack, everything, heap. But then fork has a return value. So what's the return value? So if you are the child copy, the return value of fork is 0. If you're the parent copy, the return value is the process ID of the child you just cloned. Does that make sense? And that is, by definition, not 0. Okay? So that is how the code can work. And as soon as you do the fork, what most people do is they test the return value. Is the return value 0? Then I'm running as a child. If the return value is not, then I save the copy of the child. I can wait for it. I can query what status. Did it just finish? Right? And then the child, because it does still have everything from the parent. So imagine you're the shell. I just parse some commands. Launch Chrome. That it's still in this variable. Then as a child path, you say, oh no, let me launch Chrome. Okay, so it replaces itself with the Chrome program and then starts over. And that's what exec does. Okay, so the child branch can replace itself with a specified program, and then exec will do the replacement of the program image, restart the process. Say, hey, isn't that kind of wasteful? Well, it's actually convenient this way because when you're launching, you know exactly what's happening, and it's the same copy code that can work as parent and as the initial stage of the child. Okay, and it also allows any resource sharing and other things to be controlled before it replaces. And later, but if you think that's too much duplicate copy, well, OS has a job to optimize that away. OS can only it can do optimization, but only logically telling you, yes, I made a clone, but in reality, it didn't. It's called lazy evaluation or lazy copy, copy on write. So it only gives you that illusion, yes, I made a complete copy, but in reality, it actually doesn't. Not until it's really needed. And especially if you do exec, fine, it doesn't even have to do any of that. It just has to put in these stubs in there. In case it's needed, then it does the work. You can do lazy evaluation to make this so much faster. Okay, so exec will take an argument and say which program to load to replace the clone, okay, and then restart it. So exec wouldn't return if it's successful. Why? Because it overwrites itself, right? And this is the only case where self-modifying is allowed. Well, it's not really self-modifying, it's just self-restarting, right? Oh, replacement, that's okay. But exec fails for whatever reason, then it has a return code of -1, and then global variable error no, at least in Unix environment, that has the more detailed error. Now, if you want to go and write code with exec, you're not going to find it. It's probably one of these versions. Exec LP, CL, CLE, CV, CVP, CV capital P, right? These are different variants depending on how you specify the path, argv, and any search path, and so forth. Whether you pass the argument separately with a null as the last one, variable argument length, or you pass an array. Okay, so that's really just detail. But you can do man exec to find out. Okay, so now, process creation in Unix and Linux by fork. Well, in the original Unix, yes, it actually makes a full copy of the parent. But you would do that in, say, your shell. And shell wasn't that big to begin with, so that's okay. But now programs get much more complicated, and if you want to fork something that's already huge, that's wasteful, right? So current implementation, I'll do what's called copy on write. What does that mean? That means only conceptually, yes, I returned successfully, I made a copy, but in reality, OS actually didn't do any of that. It's lazy in that saying, well, I can do memory mapping, and later we will talk about virtual memory and these memory mapping. So what it does is it keeps track of which process and it's touching which part of memory. And as long as nobody made any changes, that's okay. It does have to make a separate copy of these registers, that's for sure. But I'm talking about main memory here. So if it's still reading or executing code, no problem. Nothing changed. You can't tell the difference anyway. But as soon as you try to make a change, OS gets a trap. And then takes over and say, oh, somebody's trying to make a change. My trick is going to be revealed. Okay, so then it goes ahead and makes a copy, adjusts it, and then restore it back to you. Then the program didn't know what happened. Now it can go ahead and make the copy safely because now it's a separate copy. All right? So OS does all kinds of tricks like this to make itself do as little work as possible, but present that illusion that it made the copy. It's on demand. Okay, so this way is much more efficient because it doesn't have to do unnecessary work. And this is especially true when all you do is do an exec right after your cloning, right after the fork. Because you did all that unnecessary copying only to replace it. That's useless, right? So this is much better. So copy on write, and we'll see copy on write examples later for other cases too. Okay, so this is what a typical fork use look like. So you have main, and then you have PID. A gets fork. So at this point, so the program continues, and so main, the parent still runs as usual. Child, when it's resumed, it also runs here at the return. But then when it tests the return value A, it's gonna get 0. The child gets 0, right? So it was one copy, now 2 copies. They're both running at the same spot, but their return value is gonna be different, right? So parent will parent and child both will resume here and test, but they get different A value, right? So if not A, that means it's 0. That's child. Then it'll do print as child and exec LP this, right? Otherwise, if it's not A, that means A is now the PID of the child. And then you can do I'm the parent, and then I'll just do the wait. And in this case, it's wait till the child finishes execution, then it continues. All right. So that's kind of that magic of fork, in that you need to know both parent and child will resume after that fork, but they get different things. So this is a very typical way of doing the fork. You test, and so this does give parent a little bit initial control, because child can't just run arbitrary code, right? This is kind of that baby stage, right? And holding the baby and then feeding it, changing its diaper, right? That right after this fork, not child. This is the parent's last chance until it does exec LP. After the exec LP, the child grown up and has its own independent thing. No more control, right? Okay, so.
What happens if the parents makes how the parents make 2 childs?
Oh, yeah, it can keep doing more fork. It can do a fork in the for loop. Yeah, it can keep doing. It doesn't have to do the wait right away. It can make 100 children and then do the wait. The wait will wait on whoever finishes.
But the PID, PID number is going to be...
Yeah, you just use an array to keep them in an array. Yeah,
and all of these childs should be linked with the process PID of the parent, I guess.
Yeah, the parent will know. Yeah, as long as it's not 0, then parent knows and saves it in an array. That's fine. Yeah, you can make 100, 1,000, as long as the system can handle that many. Yeah. Okay, so a shell basically parses command, calls fork, does that, right? Instead of hardwire ls, it's whatever command the user issues, pass it to exec LP, and then launches it, right? It replaces it, and so it no longer runs as a shell. And then parent, and in shell you can do a background, right? So then that means that it doesn't just call wait right away, or it doesn't have to call wait right away. You can launch several of these. And then wait will basically block the parent until any child finishes, then continues. So process termination, there's several ways. Voluntary, that means I'm done. Okay, either I call exit, or I just finish main and falls off. What happens then? Well, if you write it in C library will link in that exit for you. So even if you don't call exit, C library calls it for you, okay? Because main is special and it knows to do that. And in any case, exit is called when you voluntarily exit, okay? And unlike our 8051 program, after your main, nobody takes over. So it just kind of runs off into Neverland. So here, there's actually the C library at work. Or you're writing a program with bug. Oh no, I'm gonna kill it. Control C. That's one way to kill it, right? Another way, bring up your task manager, select kill, right? So yeah, this is kind of violent, but it happens. And so there's a separate system called kill, or you can use the kill command, killed, and then the job number and things like that, right, from the shell. So why would you want to kill? Well, zeroth reason is you have a bug. First reason, child exceeds a resource quota, or a task no longer needed. You do something, oh no, I didn't want to do it, kill it. And then maybe another is actually what's called cascaded termination policy. So this is a policy OS may impose, which means, remember you have parent-child relationship, and suppose you're in shell, and then you started a bunch of programs, and say, oh, now I want to close this window. I don't want to run this shell anymore. Exit or close the window. What happens to all these other processes that are still running? Well, you can set it up so that it does the cascaded kill, because all these other processes were launched by this shell. Therefore, they're children or children of children, right? And by closing this window, OS may say, okay, sorry, these children, you gotta die. So kill all of them, right? So that's called cascaded. So you think of it recursion, right? Kill is parent, but then parents say, oh no, my children have to be killed too, and then go to children, and then so the whole family tree gets killed, right? So a little violent. This should be PG-13 lecture, but anyway, so there's a cleaning up to do. Right? So after these processes get killed, you just leave them around? No, you have to clean up, bury the body, right? So that means any memory allocated to them, take them back. Any open files, close them, flush them. Any I/O buffers, any I/O device occupied, release, right? Yeah.
Exit 跟 kill 的差别是一个是 parent 做的，一个是 child 自己。
No, exit is programmed by itself. Any process, a child can exit. A parent itself was a child of somebody else, right? Okay. No, anyone with permission can kill. Doesn't have to be a parent killing its children. But cascaded one, yes, it's caused by parent being killed. Then that means, oh, sorry, children, you have to die. And so, yeah, but that's OS enforces it. So, it comes from the OS, but the relationship is what causes the OS to kill its children. Okay, so the parent doesn't actually have to issue that kill. Okay, and then wait is this system call that is called by parent. You saw that example, right? And so PID gets wait of the status. So what does that mean? Your parent can fork a bunch of children, but you don't know which one terminated. So wait basically says don't come back until one of the children has something, well, most likely exit, right? So it has essentially two return values. One is returned using that the ampersand status. So that's an int pointer. So it writes the status. So that's the exit status of the child, right? And then PID means which child. Okay, so but you have to keep in mind, why call wait? Why couldn't I just fork a bunch of children and then? Well, because at least in Unix, if you don't call wait, then that means the OS won't recycle that process ID. It continues occupies that entry in the process table. And so one way to crash a Unix system is you call a bunch of child and then run it up, fill up the entire table. You don't free up any PID by not calling wait, and then it runs out of process IDs. And that's very difficult to make happen because now PID is 64 bits and it'll take you a long time to make that happen. But anyway, so the wait is kind of critical in this parent-child type of relationship in termination. So what happens if you have a child that died before its parent calls its wait? Well, that child is called a zombie. Zombie is 僵尸, right? So that dead child, right before the parent calls wait. But then, as long as the parent calls wait, it's okay. because that cleans it up quickly, right? That could happen. And now orphan processes, one, where child is alive but then parent died. And if you don't have cascaded termination, that could be an issue. So what happens? Well, in Unix and a lot of other systems, so one safeguard is that instead of parent calling wait, the parent's parent or its ancestor can call wait. And by this inheritance relationship, it could actually do a garbage collection. So go and see is a child or a children and so forth down the family tree if any of them need to be kind of buried, cleaned up, right? So, all right, so now, and you can do it all the way up to the init process, or in the case of Linux, it's called systemd. So that's one way to clean up these orphan processes, right? So the whole point with this is really somebody has to call the wait to free up that PID entry. Okay, now second part of this chapter is on interprocess communication, or IPC. You got to know this IPC. It's going to come back over and over again. So what's IPC? Well, I mean, it's kind of boring to have just one process. It's good to have multiple processes. But then, it's like, by default, they just run independently, each in its own little space. Each one thinks it has its own processor, right? But sometimes you do want processes to cooperate with each other. Why? Because for several reasons. One is for protection. Just take Chrome browser. It's organized so that your renderer and then different processing and backend, they are separately. So it's one window, potentially multiple windows, but then different kinds of tasks are done by different processes that cooperate, okay? And you may have more for modularity reason. Maybe one's producing things, one for consuming, one for a kind of intermediate stage processing, kind of a pipeline fashion. You don't want one crashing to cause the entire program to crash. That's one way. Exchanging data was one of the important considerations, but later, people start figuring out, oh, it's not just exchanging data, it's the synchronization that's the trickier part, okay? But initially, it all started with shared data, and later, synchronization became more important. And later, well, then performance also becomes important. So people started building these multiple processors, and if you have multiple processes, yeah, you run one on each processor. Parallelism, even better, right? So even if not in parallel, still you have modularity. So a lot of benefits to having multiple processes as a way to structure your program. So for convenience, modularity, speed up. Now, there's two main ways of doing communication. They're called shared memory and message passing. And you'll see these recurring themes over and over again. Shared memory basically says two processes, even though they might have independent address spaces, there's one region you can set aside and say, let's share this part of memory. And through OS's help, it's same memory, but then mapped to different parts of that of different processes. So processes still think it has its own whole memory address space contiguous, but then one part actually is mapped to the same part as another process space. And so if you write it in that region, shared memory region, the other process can see what you just wrote, and vice versa. Now that is good for processes running on the same machine, or at least share the same physical memory, because that's easy to do. And it also is fast because you deposit and then the other reads it right out. No more copying, no extra copying, right? But it gets really tricky because just when is that other process going to run? I don't know. OS decides, but does OS even have the knowledge? Unclear, right? OS just provides the abstraction. Now, message passing is probably what you'll be using most of the time. Why? Because it, first offers protection. It's much more general, works on the same machine, across machines, over the network, anywhere, right? It's and also like your TCP/IP, networking, anything like that. Yeah, it's all forms of message passing, pipes, all sorts of things. So and no conflict, but that means that the synchronization is built into your primitive. You have send and receive, but then these are not just simple send and receive. You have what's called blocking. What does blocking mean? Blocking means you call something and it doesn't return to you until it's done. I said, well, what's wrong with that? All my functions are the same way, right? I call a function, don't return to me until you finish the computing. I could use the return value. Well, yes, that's what you would expect. Blocking is the simplest in terms of programming concept, but then not simplest in terms of allowing more things to happen in the meantime, right? Because blocking means you can't do anything in the meantime, right? So message passing, compared to shared memory, is more structured. It's okay for smaller pieces of data, but then relatively speaking, you have entire graphics buffer. Shared memory is probably a better way to go compared to message passing. But if you want modularity, ability to move processes around to different machines, and then shared memory is that nicer uniform model, even though you pay a higher price. Okay, so what we'll do is separate out examples till next time, but we'll talk about these IPC models. Okay. Now, shared memory requires the two processes to establish a region of shared memory, and so they could be in the same address space or different address spaces, but whatever the case, it's mapped by the OS. Okay, and if there are different machines that don't share memory, sorry, you can't really do that. So they most likely are multi-core or multiprocessor, even if it's memory hierarchy down several levels. Remember, there's NUMA, right, non-uniform memory architecture. But in those cases, yeah, that you pay a high price. But so most likely you do this on a more tightly coupled architecture, or even single processor, right? You don't run them in parallel. You run one at a time. Anyway, so now shared memory is nice in the sense that the OS is involved only for setting up, mapping the memory. But once that's done, OS just does a context switching. It doesn't get involved in every single transaction. So I can write to the memory as much or as little as I want. OS really doesn't know that. It's mapped memory, right? No OS overhead in the actual read and write. And but the two sides have to agree on the format. Why? Because memory is just memory, just an array of bytes. How do you interpret it properly? So oftentimes what you have to do is map a struct onto that shared memory region, right? Both sides have to agree on that struct. And struct basically lays out the memory, saying this field is called, account. This field is that name. This field is something else, right? The field. So you map a struct to that raw memory, and then you can access them. And so both sides have to agree on the interpretation. There's no structure, just raw bytes. And most importantly, if both sides can do reading and writing, you have to be very careful, because I just wrote something and oops, suddenly context switch. And you didn't know I just wrote something, you wrote over. Uh-oh, so you just covered up my change, right? That's not good. So synchronization is important to be sure you don't write over somebody's changes, right? So simplest example, producer-consumer. One process could be producing something, one could be consuming. And you'll get to have fun with producer-consumer example, different versions of this. And the easiest way would be to use a FIFO. And as you know, with a FIFO, you need minimally two pointers, one for head, one for tail, right? Head is what you extract. Tail is what you append, right? So, and then circular, so that when head or tail reaches the end, you wrap it around, right? Circular buffer. And so you have an in pointer, out pointer, and so this particular scheme doesn't keep the count, but that's okay. So the conditions are if in and out both point to the same spot, then it's empty, right? And if in plus 1 modulo the buffer size equals out, then that means it's full. So in this scheme, you always, in the case of full, it's actually not full. You have one entry that's unused, but that's okay. So that's one price to pay. But at least this is one way to do this, right? And so with this kind of data structure, you can do simple producer, one consumer, and later you can do multiple producer, single consumer, or multiple, or single producer, multiple consumer, different variants. Right? So shared memory version of producer consumer. This is one for producer, and item next produce. That's just declaration in C style. Item is the type. Next produce is the variable, and then you have an infinite loop. So producer just runs in a loop. And next produce gets make item somehow. I mean, book doesn't say make item, just has a comment, but doesn't matter. And then while this in plus 1 modulo buff size equals out, that means buffer is full. That means I can't really have a space to put in my produce item. So what do? Well, book just says loop. But then here you can do a yield, and later I'll show you what yield actually means. Yield can be like in a coroutine example. Or if you use Python, it's another way for a function to kind of tentatively return some intermediate value, like a coroutine, and then later you can resume it by calling next on it. Okay, so yield in this case assumes you run on a single processor, give another task a chance to run. In this case, the consumer. Right? So why? Because by yielding, it says I give up control because it's useless for me to stay in here. Next time, when somebody else get their chance to run, come back here. Let me try again. Right? So hopefully, consumer consumes something. Next time you come back, get resumed, then that condition will be no longer true. So you don't have to wait. Right? So you fall through, and then you stick the next produce item into the buffer, increment the buffer. Now on the consumer side, right? Again, infinite loop. While in equals out, what does that mean? Empty, nothing for me to consume, right? So then you can again do a yield. Yield is more cooperative, being nice. But if you don't yield in a preemptive version, it steals control from you. Now doing yield is nicer because then it says, okay, I don't waste anybody's time, just let somebody else run. Now, hopefully, by the time you come back, in is no longer equal to out. That means something to consume. But if it's still equal, you yield again, right? And then consume by grabbing the stuff from out, which is the head of the FIFO, right? Save it into temporary or local variable next consumed, and then move the out pointer to the next position. And then you consume however you want. Right? You can write it out to UR, save it to file, whichever.
就一个是不断堆档案，然后等着别人来吃，然后一个是不断吃档案。
No, this has nothing to do with file. This is just pseudocode. If you want to map to file, you do whatever you want. Play it as audio, display as image. Any of those things can work. So this is just pseudocode. The overall general idea of the control flow. Right? Okay. Now, so that's shared memory. Message passing, on the other hand, requires not only data copying or the buffer, but also synchronization. So two primitives are send and receive, as opposed to just touching the memory directly. Now, send requires you to do like some kind of handle. Now, this handle could be a target process, could be a port, could be a mailbox, could be whatever reference. Kind of just like a file handle, right? If you write it to a file, you can't just say write. You have to say which file, right? Which you opened previously. Same idea here. So there's one argument that's the kind of the handle, right? And I'll show you some examples, the type of handle, right? So and then followed by the message, receive from H, whichever H is, and then write to buff. Buff is the address of the buffer. Now the book just says message because I guess in C syntax, if you pass an array expression, that is really just the pointer. But anyway, that's Well, and even if you put the ampersand is still here, right? Doesn't matter. And the assumption before you communicate is somebody has to establish the communication link. So there's different forms. It could be hardwired, could be dynamically established, whichever, right? So, but the general idea is the same. Now, so questions: how are links established? In certain cases, I'm going to set it up as two processes. These are all my processes, like Chrome. One's rendering, one is for network, right? So I can just hardwire those because I know what I'm doing. These work together. I just decompose them. Now, but in the case of, say, TCP/IP, that's dynamically established, right? So maybe you do a DNS lookup and then open by a name or by address, whichever. Then it dynamically establishes, if possible. If not, it tells you, no, sorry, link can't be established. Now, question is, what about these links? Can they be associated with more than two processes or exactly two processes? Well, that's up to how the communication protocol is implemented. Right? Sometimes you can do broadcast, sometimes multiple things coming in. Right? So there's different styles, and that's implementation dependent. Now, and then also between two processes, can they have multiple links, or is it just at most one? What about capacity? What about data length, fixed or variable length, or is it indefinite? Right? You just, as long as you have the link, you can keep communicating. Right? Also, is it unidirectional or bidirectional? So these are potential options you may have to specify at the time you establish the link. Okay. No, these are options. So I'm not saying you have to do it one way or another. So some systems support more options than others. And so if you want more than two processes, some may say, sorry, not supported, right? And some may require you to have only fixed size messages, others variable size, right? And then it does more work for you. And also unidirectional or bidirectional, again, that's very system specific, but these are potential options you can look for in different message passing systems. Now, implementation, so physical link could be shared memory on top. That's okay because it then packages up the synchronization for you, so you don't have to worry about whether it's really implemented with shared memory or bus link or network. Now, in terms of logic, so there's the naming concept, and the book divides this into direct or indirect naming. So in other words, do you have to name the receiving process, or the receiving process have to name the sending process? Or is it indirect where you name some common entity, then everybody just goes to there? That's loose coupling, more indirect, but maybe more modular. Symmetric versus asymmetric naming. So maybe one side names the other, but the other doesn't name. And synchrony, that's an important one. Blocking or non-blocking. Buffering. Is there buffering explicit or implicit? And is there data copying, or is it by value by reference? Direct messaging means in part of the call you have to name the other side. Are you receiving from somebody or sending to somebody, right? So the send and receive have to explicit name, but that's hardwired naming. Works with like the case of Chrome because you know exactly who you want to see. You don't want anybody else to do, right? But then it's probably not as general in the case of like a server type where you want to be able to receive from different places. Symmetry has to do with is it one-way naming or two-way naming? So in some cases, you may do send and receive name each other, or in some other cases, maybe the receiver says, I don't really want to have to name my sender because I allow different senders. So like a server would be like that, right? So then as part of the receive, it gets the sender's ID or IP address or something, some reference, right? So that would be an example of asymmetric type of process symmetry. So producer, consumer, producer would do send in a loop, maybe infinite loop, maybe finite loop, and receive, right? This is naming So this is direct communication, named explicitly, but then it has limited modularity in the sense that if you have send and receive at different places, and if you name a process change, then you have to go back and modify them everywhere. Indirect communication, on the other hand, is more like we don't name each other, the processes, who send to, who is to receive from. Instead, name some mailbox. And mailbox could be a port. Those of you who are familiar with TCP/IP, there's concept port. Or it could be some other thing in between that's shared, explicitly shared with permission. And we'll see some example next time. So instead of doing direct, you can do mailbox, send to mailbox, and then the other ones receive from mailbox. This allows you to have more flexible type of topology. Before, it may be just one-to-one. Here, you have a one-to-many or many-to-one. That flexibility, or many-to-many for that example, for that matter. But of course, that complicates the implementation of the mailbox. And so not all options are supported on all systems. It really depends on what kind, and we'll see some case studies. Mailbox would have a unique ID, and then somebody has to control the sharing. And so this the link is dynamically established, or can be dynamically established. Link may be associated with multiple processes, right? In that case, maybe one sender, multiple receiver, vice versa. And then each pair may share several communication links through maybe multiple mailboxes. And then each one can be unidirectional or bidirectional. And these options or operations include creating a mailbox, sometimes called port, and then send and receive messages through the mailbox, destroy mailbox. Okay, and then it still looks like send and receive, but A actually refers to mailbox instead of process. So if you share mailbox, there's different semantics that you have to pay attention to, right? If 1 is sender, 2 and 3 are receivers, do you allow only one to get the message, or both of them, or one at a time? And see, something like this becomes issues with TCP/IP programming too, right? So you could have one, but then multiple processes may want to read on the same port, and so forth, or different. So possible options, you could have restrictions, allowing only one link to be associated with at most 2 processes, or allow only one process at a time to receive, or maybe select arbitrary receiver, or maybe the sender needs to be notified with the receiver. These are just really just OS-dependent options or protocol-dependent options. But really, most importantly is really the synchrony, and we'll revisit synchrony many times. So synchrony refers to whether a call is blocking or non-blocking. So a blocking call is also called a synchronous call. And non-blocking also called asynchronous. But I hate to use synchronous versus asynchronous because I also teach some hardware concept. In hardware, these are exact opposite. So synchronous hardware is one that doesn't block. Asynchronous hardware is one that blocks. So go figure. Why is that? Because hardware and software people didn't always talk to each other. They use the same term. But so use blocking versus non-blocking. But knowing in software, a synchronous call is a blocking call. That means it does not return until it completes. Asynchronous is non-blocking. That means it returns immediately, even before it completes. What does that mean? That means, how do I know if it completes? I have to make a separate call to query it. Are you done? Are you done? Does that remind you with something? Yes, you are, right? With the data ready flag. That's kind of like that, except this is much more general IO, more general communication. Right? So you could do polling, you could do notification with a non-blocking. Okay, but blocking seems easier to reason with. Okay, so now you can do blocking send, blocking receive, non-blocking send, non-blocking receive. So more refined. So blocking send means send is blocked until message is received by the receiver. So it's like, but is that a good idea? Like, for example, if I send email, am I not allowed to do anything until email actually arrived and possibly read by whoever? That's not very good. I mean, that bad user experience. I send a text message, and I can't do anything until you actually read the message that shows read, right? That's not a good one, right? So people usually don't like blocking send. They like to send to go out, and you can free and go on to do anything, right? Blocking receive, that's kind of expected, right? Receive is blocked until message arrived and can be read. So if I'm waiting for you to send me something, I stare, I'm not doing anything else, right? That people kind of accept that more. But a lot of times, oh no, I don't. I just come back and wait. I do something else and then come back. Hey, did they send it to me? That's kind of polling. You could poll in a loop, or you could poll periodically. But anyway, so the blocking send, blocking receive, much stricter. And non-blocking send is more natural in the sense that I send it out and then I want a separate call to check if they actually received it or not. Okay? But that means some buffering is required. Okay? And non-blocking receive is one where I kind of do polling, check. Oh, do I have a message? No. Okay, then go and do my own thing. And if there's a message, I read it. Right? So then it does not block in either case, right? And non-blocking send, non-blocking receive. Okay. So just last slide before I wrap up, and we'll have a few more slides next time. So buffer and synchrony. So zero buffer is actually possible in this kind of send and receive. Why? Because you can do blocking send and blocking receive, and that's called rendezvous. Have you heard of the word rendezvous? And that's a French word, so don't pronounce it like rendezvous. No, it's a rendezvous. Okay, and that's a French word. You usually get that in movies, like, hey, let's rendezvous at this coffee shop, and or at military, hey, rendezvous at 1700 hour, right? So that means they meet up at a certain place, synchronize, and then they go off and do their mission. So rendezvous means whoever gets there waits for the other one, so they can both wait, but they don't need a buffer because they can do the exchange right there. Okay, so. And so rendezvous is zero buffer. Now you could have bounded buffer like our producer-consumer example. Sender is blocked if full, otherwise not blocked. Receiver is blocked if empty, otherwise not blocked. That's our typical producer-consumer. You could also have unbounded buffer. Of course, in reality, you probably wouldn't have unbounded. Everything is bounded at some point. But ideally, the sender never blocks. Receiver blocks only if empty. And so that relies on dynamic memory allocation. So that hopefully minimal blocking. Okay, I think I'll stop here and we'll continue. Oh, that's reviews. So shared memory, direct versus indirect, blocking, non-blocking. Got to know these concepts. And next time we'll see examples of actual systems that use shared memory and message passing. Okay, see you Wednesday.